In this video, I want to discuss the idea of orthogonal diagonalization. And before I can talk about how to diagonalize orthogonally, I need to define what it means to be orthogonally similar. So as a reminder, similar matrices meant that A was equal to P times B times P inverse for some invertible matrix P. On the other hand, if we want to look at orthogonally similar, we would need A to be equal to P times B times P transpose. So to diagonalize orthogonally, so an orthogonal diagonalization, so if I want to orthogonally diagonalize a matrix, I need to make sure it is orthogonally similar to a diagonal matrix. A is equal to P D P transpose. And it's actually going to be really easy to determine if something is orthogonally diagonalizable. I know it needs to satisfy this condition, and I'm going to go ahead and take the transpose of both sides here. So this would be A transpose is equal to P transpose transpose, D transpose, P transpose. Or A is equal to P. The transpose of a diagonal matrix is equal to itself. It is a symmetric matrix times P transpose. Well, this is the same thing that was equal to A. So the only way we will be orthogonally diagonalizable is if we have symmetric matrices. So if we have a square matrix A, we can say A is orthogonally diagonalizable, and there are a couple of ways we can say that equivalently. If it is orthogonally diagonalizable, it's going to have an orthonormal set of n eigenvectors. And it's also going to be symmetric. So if it is symmetric, it's guaranteed to be orthogonally diagonalizable. And any matrix that's orthogonally diagonalizable will be symmetric. And they will have an orthonormal set of eigenvectors. So to actually orthogonally diagonalize a matrix, we need to start by finding a basis for each eigenspace of A. So in other words, find your eigenvalues and your eigenvectors. Once we have those bases, we need to apply the Gram-Schmidt process to each of these to obtain an orthonormal basis for each space. We can then form the matrix P from the vectors that we constructed in the previous step in step 2. And then the eigenvalues will be on the diagonal of my matrix D in the same order as their corresponding eigenvectors, similarly to how we diagonalized matrices before. So let's look at an example. Here I have my matrix 4, 2, 2, 2, 4, 2, 2, 2, 4. We do see that this is symmetric, so we can orthogonally diagonalize. And while I will not show the steps here, you can verify that my two eigenvalues are 2 and 8. So let's start with lambda equal to 2. 4 minus 2 is 2. The second row, we have 4 minus 2 is 2. And then the third row, 4 minus 2 is 2. If I were to reduce this matrix, the first row is all 1s, and the rest of the matrix is all 0s. So my equation, x1 plus x2 plus x3 equal to 0. Solving for x1, I would get x1 equal to minus x2 minus x3. So when I write my vectors, x1 is negative x2 minus x3, x2 is a free variable, and x3 is a free variable. The coefficients of x2 are negative 1, 1, 0, and the coefficients of x3 are negative 1, 0, 1. So now I need to actually apply the Gram-Schmidt process to these vectors. In this case, my first vector, u1, is going to be equal to -1, 1, 0. u2 will be equal to -1, 0, 1 minus the dot product between these two vectors, which is -1 times -1 is 1, 1 times 0 is 0, and 0 times 1 is 0. So the norm of u1 squared would be -1 squared plus 1 squared plus 0 squared, which is 2, times u1, -1, 1, 0. And if we work this out, we would get -1/2 -1/2 1. We still need to go one step further because we do need these to be orthonormal. We know the length of u1 is equal to 2, or the length of u1 squared is equal to 2, so we need to multiply the first one by 1 over the square root of 2. That would give me -1 over root 2, 1 over root 2, 0. So this is the first vector that I'm going to need for my matrix P. If I try to find the norm of u2, I would have the square root of -1/2 squared plus -1/2 squared plus 1, which works out to be root 6 over 2. So I would need to divide by root 6 over 2, or multiply by 2 over root 6 times my vector, which would be -1 over square root of 6, -1 over square root of 6, 2 over the square root of 6. So this would be my second vector that I need for my matrix P. Now that we've got those, we need to check what happens with my other eigenvalue, which was 8. My original matrix had 4s on the diagonal and 2s everywhere else, so 4 minus 8 is -4. 2, 2. 2 minus 4, 2. 2, 2 minus 4. Whenever I reduce this matrix, I get 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0. So my equations, x1 minus x3 equal to 0, and x2 minus x3 equal to 0. In other words, x1 is equal to x3 and x2 is equal to x3. And we can see one possible solution to this is 1, 1, 1. We do need to normalize this vector since we do need an orthonormal basis. Since its length is the square root of 3, I need to divide by the square root of 3. That'll give me 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. So now this will be my third vector for P. So now I can finally write my matrix P. My first vector that I found was -1 over the square root of 2, 1 over the square root of 2, 0. The second one was -1 over root 6, -1 over root 6, and then 2 over root 6. The third one, 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. The matrix D, the first two eigenvectors in my matrix P came from an eigenvalue of 2, and the third came from an eigenvalue of 8.